somebody asked, will the lecture be recorded? And the answer is yes. I just pushed the recording button and that should show up on your screens as well. So just for the recap of the recording, here's how we started. And this was the recap from last time. And then we led into what we're going to do now. Okay, so let's now proceed. So what I want to do next is I want to look at what happens for t greater than Tc. So this is my claim, and I'm going to show you how this all hangs together and is self-consistent. So my claim is that for t much larger than Tc, and certainly, in fact, actually larger, the first term is negligible. But for t less than Tc, the first term is important. And the way that we're going to see that this is true is from doing, again, a scaling analysis. So the idea is do a scaling analysis for the thermodynamic limit. And so what that means is that we're taking n going to infinity, we're taking the system size going to infinity, and then we're keeping n, which is n over v, fixed. So that's the thermodynamic limit that we've talked about, and that's how we're going to establish these facts. So let's see how this works. So let's consider what happens for t less than Tc. So for t less than Tc, what we know is that mu is certainly very small. And I've written very small in quotation marks because we actually need to find out what does very small actually mean. So let's just for a moment leave that question open. We're going to say that t is very small and mu is certainly very small and also negative. So what we are going to do is expand the first term. So that first term is the one that is over here. So this first term, which represents the ground state energy, or the ground state contribution, this is representing the excited states. And that first term is then, I'm going to call that N0. So that's just simply expanding the exponential, and then that is then going to be the ones conveniently cancel out, and what that means then is that n0 is essentially minus kBt over mu, and so so if mu is scaling of order is scaling of order 1 over v, which is the same thing, of course, as 1 over n, because the density is fixed, then what that means is that then n0 over v is then going to be a quantity of order unity. And by saying it's a quantity of order unity, what that means is that it doesn't, it just stays as a constant as I take the limit n goes to infinity and v goes to infinity. And so this is going to be our claim that mu is small, and how small it is depends on the size of the system. And asymptotically, as the system size goes to infinity, keeping the thermodynamic limit, mu is getting smaller and smaller, but scaling like 1 over n or 1 over v. And if that's the case, then the number of particles in the ground state is also scaling like that. And so n naught over v is of order unity. And we say when this is true, we say that the ground state is macroscopically occupied. Now, when we say macroscopically occupied, we don't mean that it has a large number of particles in it. What we mean is that the way the number of particles scales with n is proportional to n. So this macroscopic occupation means something very specific. This is not just a large number of particles. It is a non-zero fraction of particles as you take the thermodynamic limit. So, this difference between number and the scaling is the important aspect of macroscopic occupation. So the macroscopic occupation corresponds to the fraction and not the number. Okay, so that's the important thing. So people often confuse those two. Okay, so that's the idea then of macroscopic occupation. So what I've shown you is that if mu is scaling in this way, then we can get macroscopic occupation of the ground state, meaning that there's a non-zero fraction. So let's have a look at the excited states. So the next question: what is the occupation of the excited states? For T less than Tc. So here's how I'm going to estimate that. What we're going to say is, remember that the energy is just, these are ideal particles. So the energy is just h bar squared k squared over 2m. And remember that k goes like, the k vector goes like pi over L times the quantum numbers. So what that means then is that k, so that k scales like 1 over L, which means k squared scales like 1 over L squared. And what is L in terms of the volume of the system? Well, the volume of the system is L cubed. And so what we've learned from that then is that the energy of the system is scaling as v to the power minus 2/3. So now let's work out what is the occupation of a single quantum state with energy k. So I'm going to compute the expectation value of a occupation value of a state with energy epsilon of k, and therefore with wave number k. And so that we can just read off from the Bose-Einstein distribution. So that's equal to that. And then we can expand the exponential. So this is essentially 1 over beta epsilon. And what I'm going to do is I'm going to take this factor epsilon out through here. So we know that mu scales like 1 over v. We know that epsilon scales like 1 over v to the 2/3. And so then this thing is scaling like beta epsilon over into 1 plus something that scales as v to the minus 1/3. And so that means that that expectation of n scales like v to the 2/3. Okay, so that's great. So now I want to work out the fractional occupation. So the fractional occupation So that's the expectation of nk over v, or equivalently over n would be the same thing. That scales like v to the minus 1/3, and that then goes to 0 as we take the system size going to infinity. So what we've just seen then is that the ground state, which is a single quantum state, is macroscopically occupied. For t less than Tc. The excited states, they are not macroscopically occupied. On their own, but collectively they are macroscopically occupied. And so that's what. So the ground state is something special. So this is the meaning of what we call a condensate. So in fact, as we go to 0 temperature, what happens is more and more particles occupy the ground state. And we can now go ahead and calculate that. So the next question then is how do we calculate this correctly? Okay, well, so that's easy because we can do a trick. And the trick is this: when we're less than Tc, we saw that mu and the energy scale in different ways. So for T less than Tc, we know that mu scales like 1 over v, epsilon scales as v to the minus 2/3, and so therefore mu over v scales like order v to the minus 1/3. And so what that means is that we can neglect the factor mu with respect to the factor epsilon in the Bose-Einstein formula. So of course, always the difficulty when you're computing in ground partition function is taking into account the chemical potential. But we can see that with respect to the Bose-Einstein formula, so if we're computing, if we're writing that n is equal to n naught plus n epsilon, and this epsilon here means excited states, then this thing here is the contribution from the ground state, and n epsilon is just the following. It's just our usual formula that we wrote down a couple of screens ago: 4 pi squared over 2n over h bar squared to the 3/2, the integral from 0 to infinity, epsilon to the 1/2 T epsilon, and then our Bose-Einstein factor, which should be e to the beta epsilon minus mu minus 1. And of course, this mu is a function of temperature, so it's a complicated thing, but we can see that mu is scaling less than epsilon. It goes to 0 faster than epsilon as we take the thermodynamic limit. And so therefore, we can cross out that term over here. And so now what we're left with is just this term in the exponent. And because we're only left with that term in the exponent, then we can do this integral. And we can do this integral by scaling out beta by changing variables. And so, so therefore, in fact, what this integral is then equal to, this is the same integral that we did to work out the critical temperature. But when we did the critical temperature, that beta was beta C, which is 1 over kBTC. But what is happening here what we have is that beta is just 1 over kBT for any temperature less than Tc. So we already know what this integral is, and so we can simply then write down that this, just read off our results from before. So n epsilon then is going to be 2.6 times the volume m kBT over 2 pi h bar squared to the 3/2. And it's exactly like what we had before, but before we had Tc, and this was the equation that defined Tc, and n was replaced by the total n. And so then we can write this then as just n times T over Tc to the power 3/2. And so then that allows us to then compute by just subtraction what is the number of particles in the condensate. So therefore, n0 is then the total number times 1 minus T over Tc to the 3/2 power, just like that. And so what you can see then is as we go below Tc, the number of particles in the condensate grows from 0 in the way that this shows here. Kind of like what you might expect to have seen in a second order phase transition. Some of you may be thinking this is like the order parameter, like say a magnetization as you go below Tc. But this isn't actually a second order transition. And for the reasons for that, you're going to see in the next homework, where you're going to in fact find out that this is not a second order phase transition or third order one, as sometimes is claimed, but in fact is more akin to a first order phase transition, and you'll actually compute the latent heat at the transition. So this tells us then how n scales. Okay, before I go on and calculate the energy and heat capacity, any questions from the class? Yes, Mingwei Liu raised a hand, so please unmute your mic and go ahead with your question.
Does the same technique could be solved the massless boson, like photon, or any?
No. So that's a very interesting question. So your question is, can we do the same thing for photons? So in the I have today, you will get to these two photons and I have this topic in this section. But in fact, the photons actually we'll get to that in just said the microphone is not working. It means my microphone is active. Are you guys having difficulty doing my microphone?
We can hear you clearly.
You couldn't hear the answer clearly. Okay. Let me try again. So I asked the question that you get us to apply these ideas from and that in I understand my audio includes okay, I've switched to a different microphone. Is this one better to everybody? Much better. Okay. All right. So apologies for that. We'll try sticking with this microphone then. Okay. Can you hear me now? Okay. All right. Thank you. Actually, this thing, yeah, there's a warning here. It's telling me, I don't know why it's doing that. Okay, you can still hear me, right? I didn't mute myself again. Good. Okay. All right. Thanks for bearing with while we get these teething troubles sorted out. Okay, so let's proceed with the calculation. So now we've worked out the ground state. So now I want to work out the energy and the heat capacity. Okay, well, we know we can calculate the energy very simply because that's just the expectation value of the energy. So all we have to do is do the usual density of states integral. Now putting in the epsilon, that's what we're trying to compute. And then because we're below TC, we can ignore the chemical potential in the Bose-Einstein factor. So again, there's no chemical potential over here. Wait, Professor, please could you, I'm sorry about this. Professor, please could you repeat the answer to Ming Wei's question on photons? Yes, the question, I will do that. The question was, can you get the same analysis, can you apply it to photons? In other words, can you get this Bose-Einstein condensation of photons? And the answer is, you're going to look at the connections between Bose-Einstein statistics and Bose-Einstein condensation for photons in a future homework. But the answer is fundamentally no. You strictly speaking cannot get a Bose-Einstein condensation for photons. And in the homework, you'll get to figure out why that's the case. So I'm not going to explain any more. Hopefully that's good enough for you for a moment. Okay, so now we have to just simply do this calculation. And so when we do it, let's figure out what it's going to look like. So the first thing is, for those of the, so what I'd like you to do, if we were doing this in class, I would say at this point, write down on a piece of paper how this is going to vary with temperature. Because you can see here that we have this factor epsilon over kBt. So the way we're going to do this integral is by the usual scaling trick, is to make a change of variable. So you should be able to work out for yourself how this thing depends on temperature. So please, I'm going to pause for a minute. Please take a minute to without doing any calculation, just look at the integral and figure out how it's going to scale with kBt. So it's going to scale as kBt and to some power here. And so with somebody in the class, tell me what the power is. Okay, so we've got a bunch of answers. So Shreya says 5/2, Steve says 2, Ryan says t squared, Cheng Yao says 5/2. Okay, so thank you. So the actual answer, so who said the power 2? Who said the power 2? Let's see, Steve and Ryan. Can you say why you thought it was the power 2? And you can unmute your microphone and speak if you wish. I didn't hear anybody speaking. Because of the epsilon and the epsilon. That's right. That's those factors are there, but there's another factor that you've forgotten. There's also a power that comes from the density of states and energy. Yeah, exactly. You missed the fact power from dV. That's right. So the actual answer is that this thing is going to go like kBt to the power 5/2. And then the other factors that go into this are a factor of v over 4 pi squared, 2m over h bar squared to the 3/2. And then after I've taken out the factor of kBt, I have the integral x to the 3/2 dx over e to the x minus 1. And so so that's just some number. The upper limit should be infinity in the upper integral. Yes, it is. It is infinity. Vibhav has a question. Wait, yeah, my integral does, oh, this integral. Yeah. Yeah, you're right, thank you. Yeah, that's right, in that integral I made a typo. Exactly. Okay, so then you can work out what this thing is, and it's about 0.77 nkb t times, well, well, I think there's a misprint in my notes. It's either 5/2 or it may be t times t over tc is the 3/2. I'm not sure. I made a there's a typo. So maybe this. So you can check it. Okay, so that's the internal energy, and if we compute the heat capacity, then the heat capacity at constant volume is just 1.9 nkb t over tc to the power 3/2, and that one is correct. Okay, so now let's see. Okay, so now let's draw this. So on the vertical axis, on the horizontal axis, T over Tc, on the vertical axis, I should say, Cv over N Kb. And if we had a classical gas, this would just be a constant, and it would be like 3/2. Then let's put in Tc is equal to 1 over here. And then what this curve looks like is something like this. So this behavior here is this T to the 3/2 behavior that we've just calculated. So the heat capacity of an ideal Bose gas is considerably different below Tc from the heat capacity of an ideal classical gas. Now this thing here is a slope discontinuity, as you can see. And so somebody might say, what is the order of this transition? And that's a very good question. Are we seeing here a phase transition? And you might say, well, it should be. Why not? So then, what order? If so, what order? So let's just remind ourselves how we describe the order of phase transitions. So the order of a phase transition was classically defined as the derivative of the free energy that has a discontinuity. So, for example, if you have say melting or freezing or liquid gas, so this gives you a discontinuity in the first derivative of the free energy, and so that it's a discontinuity in the entropy, and so those things are called first order transitions. So here, well, what do we have? We have we have the heat capacity, so that's T ds by dt, and so that would say that a discontinuity in the derivative with respect to temperature of C, that would be a third order transition. And so that's the claim, but it's not true, and you have to do a more careful analysis to see what's actually going on, and that's what's going to be in the homework. Now, the other thing you might say about it being a phase transition is that phase transitions usually result from interactions. And we're going to see that later on in the class. We're going to see specifically how collective effects, interactions between particles, or degrees of freedom give rise to collective phenomena and phase transitions like magnetism and so on and so forth. But here, there is no interactions. Because what we're dealing with is free bosons. So what we're seeing again is that the quantum statistics essentially gives rise to some effective interaction and this is strong enough to cause a phase transition. So we've now got two things that we saw. So in summary, when we were dealing with fermions, what we computed was the lowest quantum corrections to ideal gas using perturbation theory. And then what we just did for bosons was we showed that there's actually a phase transition. And in both of these cases, these are due to quantum statistics. So this idea that statistics can lead to interactions is one we've seen now in both of these examples that we've done. And also we've seen that interactions can have two different effects. One is a weak perturbative effect, which you can compute by perturbation theory, and it gives you a perturbative small correction to some other behavior, such as the classical behavior. The other thing interactions can do is they can actually lead to a qualitative change in the nature of the system, that is, cause a phase transition. And when we get into the next chapter in the course on interacting systems, we're going to explore this explicitly, both doing diagrammatic perturbation theory for the first one and the theory of phase transitions for the second. Okay, so let me just conclude this section with some comments. So the first comment, actually the main one that I want to make is what actually I really make this comment. What was the other comment I wanted to make? Oh, I know what it is. So the comment is this: what is the effect of interactions? So now let's suppose that we're not dealing with ideal bosons, but we're dealing with interacting bosons. So the answer to this is take my course, Emergent States of Matter. And possibly taught in maybe it's, I don't know if it's taught in one of the other condensed matter courses in the system, but what you're going to see is in that course, hopefully it'll be offered next year, in the Emergent States of Matter course, what you'll see is that the transition is a second order transition, not a first order one. And this transition underlies the superfluid, superconducting transitions. It's not identical to it, it underlies it, and is observed in atomic gases. So we understand this very well. Okay, any questions about that before I go on to the next topic in this section on ideal systems, which is ideal magnetic systems? So any questions? If you have a question, raise your hand and then unmute your microphone and ask your question. Okay, looks like we're good. So let's move on to the next topic. So what we're looking at now is we're going through our list of systems that we can solve exactly analytically. So what we're going to do is now switch gears, and we're going to talk about paramagnetism. And what I'm going to do is I'm first of all going to do it classically, and then I'm going to do it quantum mechanically. So this is now going to be the first example of a system where there's no translational degrees of freedom, but there are internal degrees of freedom, the most famous one is the Ising model, which is our sort of benchmark system for looking at systems that are interacting. But what we're going to look at now is the ideal gas version of a magnetic system, i.e. one with no interaction. So the goal in this section is the following. We're going to look at a system where there is no translational degrees of freedom. And then we're going to look at the as a simple magnetic system that is the counterpart to an ideal gas. And then this is a preparation for dealing with interacting spin systems. So what is the actual physical system? So let's draw our box. So here's our system, and now what I want you to imagine in it is that I have a bunch of magnetic dipoles, as shown like that, and then they are in principle in an external magnetic field, and that external magnetic field is oriented along the z-axis, so that this is x, this is x, and this is y. So that's our system, and what we're going to have is n dipoles, and they have magnetic moments. So mu I goes from 1 up to n is the magnetic moment, and then we have an external field H. And what we're going to assume is that these are non-interacting dipoles, non-interacting spins, and the experimental realization of this is the so-called dilute paramagnetic salt. So since I'm going to be showing you a comparison with experimental data in a minute, let me just list what those are. So these salts would be things like this thing. Now I'm going to have to copy down the formula carefully. Make sure I get it right. So this is one. Here's another one. And then the last one is this one, this gadolinium salt. And these are different. These different salts have been chosen as specifically. I'm talking about those because they have different valence states. So the paramagnetic ion in each of these cases is the one I'm underlining now: the chromium, the iron, and the gadolinium. And in fact, what the actual state, valence state of these ions. So this is a chromium 3 plus. This one here is an iron 3 plus, and this one here is a gadolinium 3 plus. If I got this right. So what we need to know then is what the angular momentum states are that correspond to these ions. And for that, you need to do a bit of quantum chemistry. So, but I'm just going to tell you what the answer is. So for these ones, for the iron and the gadolinium, it turns out that they are in an L equals 0 state. That's the orbital angular momentum, and then the total angular momentum is just the spin, which is 5 halves and or 7 halves respectively. So it's 7 halves for the gadolinium, and it's 5 halves for the iron. And then for the chromium, it turns out, for reasons that I had difficulty in understanding in detail, but I believe are correct, is that the angular momentum state there is 3 halves. And the reason why that one's complicated, for the iron and the gadolinium, when I went through the arguments for those things, that was easy to understand with basically high school chemistry and simple rules for valences. For chromium, you get the wrong answer if you do that. And what you have to worry about are crystal field effects. So that's not what I want to focus on, but we'll just take that as a given. Just as in all statistical mechanics problems, what happens is you do a quantum mechanics problem first, and then you do the statistical mechanics. All right. So what do we expect? What is our intuition then about the behavior of the system? So we're going to think about this at low temperatures and high temperatures. So what we expect is that at high temperatures, and I'm going to put quotation marks around that because as physicists we know that you always have to say high with respect to what, and I'm going to answer that question precisely in a couple of minutes. So but at high temperatures, well, what do we have to think about? Well, the thing that we always think about in statistical mechanics is the Helmholtz free energy and the balance between the energy and the entropy. So what's going to happen is that if I'm at high temperatures, then the TS term is going to be the one that is more important. And because that term is more important, what's going to happen is that the spins will point in all directions. And that means that there will be no net magnetization. No net magnetic moment. Now what happens at low temperatures? So at low temperatures, it's going to be different because at low temperatures, what's going to matter is the T term is going towards 0, and so what's going to be important is the energy. And actually, what is the energetic term? Well, the only energy in the system is the interaction with the field. And so when you apply an external field, what's going to happen is that the spins are going to try to align parallel to the magnetic field, and so the only interaction of the spins is the spins with the external field, which will align them. And that then is going to give you a net magnetic moment. So what we want to do is to calculate the magnetization. So that's essentially what we want to compute. Okay, so let's set this up. Well, of course, everything starts off with a Hamiltonian. So now let's write down the Hamiltonian for the system. And now all we have is the magnetic moment, mu I, sum from I equals 1 to n. And they are going to interact with our external magnetic field, excuse me, that is pointing in the z direction. And so I can write this as minus mu times h times the sum from I equals 1 to n of cosine theta of I. And what is theta of I? Let me draw you a picture. So theta of I is the following. So here is my polar coordinates. Like so. Now I'm going to imagine that my magnetic moment is pointing out like so, and then the angle with respect to the z direction is theta, and then I can project this down onto the xy plane, and then this angle here is the spherical polar angle phi. And so this is true for each spin, and so then I can just write down the partition function as the sum of the cosines of those angles. So what I want then is to compute the partition function. So z for n spins is the trace of e to minus beta h. And I want to say what I mean by this terminology, trace. So what trace means, it is adapted from quantum mechanics. So if I wanted to write this thing down in quantum mechanics, this would literally be the trace of the density operator times the of the system. So what we mean by trace is sum over all degrees of freedom, whatever they are, for the problem of interest. And so in this case, when I write down the notation trace, what I really mean is a trace over the degrees of freedom, and my degrees of freedom are the thetas for the spins, and the thetas for the spins, and the phi values. And so what I really mean is I sum over all values of theta 1 and phi 1, sum over all values of theta 2, phi 2, and so on, all the way up to theta n, phi n. And when I write down the sums, I'm just being formal. So these sums here may well actually be integrals. Okay, so that's just a notation that I'm using. Okay, so we'll get to that. So now we can see that the Hamiltonian is just the sum of terms. The trace is a product of these terms over here. So what that means is I can write down that the partition function is going to be a function of beta. It's going to depend on the external magnetic field H. And so this is going to be the sum of theta and phi for all the particles. And then e to the beta mu h, and the sum over I equals 1 to n cosine theta I, like that. And now I can factorize this. So this is then just equal to the sums over the thetas and phi's, and then the product from I equals 1 to n of e to the beta mu h cosine theta I. And then I can write this as the product from I equals 1 to n of just the partition function of just theta I phi I e to the beta mu h cosine theta I. And what I want you to notice in this term here is that this is called theta I. This one is called phi I. The phi I doesn't appear, but that's just because of the symmetry of the problem. The theta I appears here, but the theta is just a dummy variable. I could call it hippopotamus or walrus or anything I wanted. So this thing here, this is just a dummy variable. And so what that means is that what is in the curly brackets does not depend on I. And if it doesn't depend on I, then this whole thing factorizes. So then this thing is equal to the partition function for one spin just raised to the nth power. And so the factorization is the expression of the fact that this is an ideal system. And so now what we have to do is calculate the partition function for one spin. And what that partition function is the sum over theta and phi e to the beta mu h cosine theta. And now I can just simply write that as an integral. So it's the integral from 0 to pi d phi, the integral from 0 to pi, not cosine, mistake there, sine theta t theta. So that's the measure in spherical polars. And then the thing that is my integrand is e to the beta mu h cosine theta, like that. And so all we have to do is do that integral, and it's easy to do for the following reason. So this I can write as follows. This is just 2 pi. That's doing that integral, and then I can write this integral from 0 to pi sine theta d theta. I can write that as d theta times d by d theta of e to the beta mu h cosine theta. When I take the derivative with respect to theta, that's going to bring down an extra factor of beta mu h sine theta with a minus sign, and so I have to divide by that. So this is times 1 over minus beta mu h, like so. And then because this is now a perfect derivative, I can just straightforwardly write out what the answer is. So this then is just going to be 4 pi times the hyperbolic sine, so shine, of beta mu h divided by beta mu h. So that's the partition function for one spin. Now the thing I want to compute is the magnetization. So the net magnetic moment or net magnetization, as we call it, in the z direction. So that is just the following. I take mz. What I want to compute then is the sum over all the spins of the expectation value of the magnetic moment dotted with the unit vector in the z direction, and then that is equal to the expectation value of the sum over I mu cosine theta I, like that. And then I can write that as a trace. So this is the trace over my degrees of freedom theta of the sum over I mu cosine theta I. So that's my thing there. and then my Boltzmann factor, so e to the beta mu h sum over I cosine theta I, and then normalized by the partition function, which is just trace of e to the beta mu h cosine theta I. Like so. And so how do I get the magnetization? Well, we're going to use our usual trick. So you can see that this factor here is the same as this factor up here in the exponent. And so what that tells us that we can compute the magnetization by just taking the derivative with respect to the external magnetic field. So then this is just 1 over beta dZn by dH divided by 1 over Zn, and this is then just 1 over beta d by dH of the logarithm of the partition function. So this is the partition function with n spins, because this is the total magnetization for the n degrees of freedom in the system. Okay, so now we know that the partition function factorizes. So because Zn is just Z1 to the nth, that means that the magnetization in the Z direction is then just n times 1 over beta d by dH of the logarithm of the partition function for one spin. So the magnetization, as makes sense, is proportional to the number of degrees of freedom. So what I've got to do now is I've got the partition function for one spin. So there it is, there's Z1. And so what do I have to do? Well, I just have to differentiate this with respect to H, and H appears here and here. So I'm going to get two terms, one that comes from differentiating psi, which is going to give me a cough, and another term that comes from differentiating this. And so we can do the derivative, and then what you get is that the magnetization in the Z direction is n times the magnetic moment of the spins times this function, cough of x minus 1 over x, and x is equal to beta times mu times h. So what beta is, what x is, this is just the ratio of the magnetic field energy, of the magnetic energy, divided by the thermal energy, and it's dimensionless. So now we can ask, what does this thing look like? So what we can see is, now let's work out the asymptotics. So what is the asymptotics? Well, to work out the asymptotics, first of all, we look at the regime where x is much less than 1. And for x much less than 1, what does that mean? That means that either h is small or t is large. So we either have a weak field or high temperature, but they're both the same thing. And in that limit, so what happens? So what we get is that cough of x minus 1 over x turns out to be x over 3 minus x cubed over 45 plus order x to the 5th. So that's that. And then for x much larger than 1, so x much larger than 1, that's going to be h is large or t is small. So either we have a strong field or we are going to very low temperatures. And so then what happens is that cough x minus 1 over x is equal to basically 1 minus some correction terms that are going exponentially with x. And so what that means is that in in the limit, in the weak field limit, which means h is small, then what we get is that mz is scaling like n times mu squared over 3 kbt h plus higher orders in h, and this is what you would expect. This is a statement of linear response, which we'll talk about more in the course. And what I mean by linear response, what I mean is that I apply an external field, and there's a response, and that response n is proportional to the external field, which is what you would naively expect. We will slightly get into this in part on phase transitions, but we'll see that linear response theory breaks down along with the rest of statistical mechanics when we are near a second order phase transition. So going back to this weak field limit, I can then compute the susceptibility. So the susceptibility, the weak field isothermal susceptibility, what does that measure? So what that measures is how strong the external field needs to be to move the magnetization. So that's basically just defined as the small h limit of dmz by dh, and that is equal to m mu squared over 3 kbt. And this is a law that's known as Curie's law. Marie Curie, who won 2 Nobel Prizes. Okay, so that's the magnetic system. Just a point of nomenclature here. So this function here, we're going to come back to that. This function is known as the Langevin function. Langevin has both a function and an equation, and this comes up a lot. It comes up also not just in magnetic systems, but in making models of polymers. So it's just I've got a little bit of room here. So why don't I just sneak in what a graph of what the magnetization looks like as a function of x. So this is mz over mu n, and so what we've seen is that it asymptotes to a value 1 at large values and then goes up linearly like that. So that's the magnetic behavior of the system. Okay, so the next thing I want to talk about is the quantum paramagnet. So I propose to leave that to next time, since we're nearly out of time. So paramagnetism, the quantum theory. So we'll resume from there. So just to summarize, so what we've seen today, we've seen how Bose-Einstein condensation occurs, and we've seen how the chemical potential varies with temperature. I'm scooting up here because there's a picture I like to draw. I don't know if I drew it. Let me see if I can find a space where I can sneak it in. Nope, I can't. So let me just add that down here at the bottom. Terrible blackboard technique. Well, we can do this. We can do this because we're It's easy to do quickly. So just as a summary of today's lecture. So this is a graph that I wanted to draw, but I forgot. So this is for temperature for bosons. I want to plot what the chemical potential looks like as a function of temperature. So we started off oh, I know why I didn't do it, because I had it right at the beginning. That was my evil plan. Let's go back to the first one, and let's put it in here. So I'm showing you the picture here. This was how we started the class with the chemical potential as a function of temperature. The blue one was what we expected. The yellow one was what we calculated last time, and in fact, neither of these are what is really going on. So let's try to draw what is really going on. So what's really going on is it's kind of a mixture of the two. It's kind of coming down like this, as it's on here, and then once it gets to this point, then it sort of changes a little bit and does go in to the zero like this. So this one here, the green curve, is the actual thing. What is the difference between this one and the blue one? The difference is that this gap here is a gap that is scaling with the system size as 1/v. So the chemical potential goes down as a function of temperature until it gets to within about 1/v of the system size, a value that scales as the system size gets bigger and bigger, and then there's some sort of change of behavior, and it goes towards zero, reaching zero only at t equals 0. So basically, then everything works as we had expected. So that was the behavior of the Bose gas, and turn this to the top. There we go. And then what we saw then that the statistics give rise to the quantum statistics give rise to an effective interaction, just as we saw with the fermion case. And then lastly, we did the ideal classical paramagnet, and we saw how we can how the system factorizes, the partition function factorizes, and we can compute the response. Okay, so any questions about today's lecture? Okay, looks like everybody understands everything. The colloquium starts at 4, and that's virtual. And somebody shared the link in the chat window, so you can all go and join it by Zoom now that you have it. Anybody have any comments about the experience of receiving a lecture over the internet, about the virtual lecture? Did things go reasonably well from most people's point of view, apart from the early snafu with the microphone? Okay, so a couple of people saying, yep, it was pretty good. Mark says it's harder to pay attention. Yeah, okay. Anything I can do to make it easier to pay attention? Nope. Okay. One thing, yeah, I don't know. Yeah, I do understand with the APS meeting last week, you have this similar kind of experience. I don't know what to recommend. Maybe wear headphones, have a bigger screen. Yeah, you fell back. Somebody wrote, I fell behind a few times, couldn't look back at what you wrote previously, which was difficult. Yeah, that's true. Now, I did record the lecture, and I will put it online, and I will send you the link so you can recover it afterwards. And the other thing that I can do is, if you would like, I can make a PDF file of today's lecture, and I can email that to you. Would you like that? Mark says that would be great, and Nathan says yes. So that means the video would be great, and the and the lecture. Okay, great. So I'll do that and watch for that, and I will also be sending out the next homework with instructions of how to turn it in. You'll have to do it virtually, I'm afraid. Okay, so please go to the colloquium and take care. And this is the last time I'll see you before spring break. So have a good spring break. Okay, so I'm going to end the meeting now.